ahead. My name is Daniel Kazempur. I'm postdoc at the Christian Albrecht University of Kiel, Northern Germany, University by the Sea. And I'm delighted to have you all here in that course, online course, and maybe also see you in Gdynia or Gdansk. Yes, let me share the screen. I asked Audrey if she can also share the slides afterwards or send them to you that you have them as well. Because from my side, it shouldn't be a problem. Yep, now sharing the right screen. There we go. And here. There we have it. And I think, oh no, that was Control L for the entire screen. Yeah, there we have it. If you have any questions in between, please feel free to ask right away within or during the talk, because in this list of Zoom, it may be that I overlook or just speak up. So no worries on that. Yeah, so this one is together with my advisor, Professor Per Krüger, and it's on managing and processing big scientific data. I mean, the big part is what we get in our big data part is in the second half of this presentation. So what is this lecture, or what is it not, to put it in this way? Oh, I see something in the chat. Okay. This lecture is primarily to give you some kind of like overview, the big picture, instead of some low-level details. And what we give you at hand is what is here in the wild to handle scientific data, and what are kind of like pitfalls to take care of or to pay attention. And as mentioned, if you have questions, go ahead and speak up. And if you're interested in more details, here's written, feel free to contact Per Krüger. This is done to kind of like to troll him a bit. No, I mean, he will be delighted to get the questions, but also me as well. It's not PKR, my is DKA for Daniel Kazempur, DKA instead of PKR. Feel free just to ping us. If we reply a bit late or a few days later, it's not that we are like, we get an email, but it's because we are occupied by some other meetings or some deadlines. So just for the record, that we are on that. Well, why should we care about all this, about that lecture that we have here? And well, that's a long road. So from the raw data that we get here up to the final, to the knowledge, to the insights that we gain, there is a whole pipeline. And this pipeline is actually quite old. One would say even almost vintage from data mining machine learning perspective. It's from Fayad et al. From 1996, the so-called KDD pipeline, or the KDD process. And it states that we have in the beginning a database with some information repositories. Then we do on that data some data cleaning, because there's some outliers, some noise, some faulty data. Imagine you have some sensors, the sensors are broken. And we have also some integration. Integration in which sense? You may have data from different sensors. As a concrete example, we were working with people from biology, and they had gene sequence data, and we're like, easy as apple pie, we just put them together, no big deal. And they said, sorry, can't do. Why that? The reason is their gene sequencing has been done by different sequencing methods with different parameters. And that meant that we could not simply put together all this content, but instead had to pay attention of if we can then merge at all, if we can integrate this data together, and if yes, under which conditions, what we have to pay attention to. After having a nicely cleaned and prepared data, we've got this data warehouse, or nowadays also data lakes. And on this data from data warehouse, we can do some transformation, selection, and projection, meaning that, for instance, we select only those entries that satisfy a certain criteria. For instance, only those entries where the temperature of the water is above 20 degrees or 18 degrees, or selecting only the column of temperature or carbon dioxide of the seawater and omitting all other columns. This would be like a projection. On the other hand, it would be a selection if we filter by rows and not by columns. So in the end, we see it's melting down. We have only some task-relevant data. And on that task-relevant data, depending which task, if you want to find clusters, and it's a clustering task. If you want to train a classification a method like a support vector machine, then it's a classification task and so on. And on this, we can perform our data mining and obtain patterns. Patterns like clusters, patterns like optimal separating hyperplanes, and so on and so forth. And from that, we can conduct some visualization, or even from task-relevant data itself, we can perform a visualization. And then domain experts, people from biology, chemistry, marine science, whatever, the whole range, they can look at the data and hopefully gain new insights, but also, and that's the cool part about research, coming up with new exciting questions. And we approach this whole thing first by what is big data? And this is some shiny prospect content that we have here. McKinsey in 2011, from a business perspective, said here, this is like the new oil, data is the new oil, and we have to dig into this wealth of data and control it and make it ours and whatnot. We have here this technical perspective also that we say here we have the means now to discover patterns, solid or robust patterns through this massive amounts of data. And well, today we pay with data to a certain degree. So we all well know, like Facebook or Meta or Alphabet, Google, and X or Amazon, they using the service means we provide data. Whenever I go on Amazon and click for a book on recipes on double chocolate cookies, it means they gain some information from me that, okay, this person is interested in double chocolate cookies, which I indeed have purchased, not double chocolate cookies, but cookies in general. And then we have like data is used to improve service target advertisement so that you do not get, as someone who has no affiliation, no passion for tennis, you keep getting tennis advertisements, targeted ads through your preferences by browsing. So data is sold. Data is as a means, data is something from which like with which money is made. And over all these years, it has been rediscovered, and we have some synonyms. We have data science. Nowadays, it's artificial intelligence, AI. The coolest kid on the block is the term. We have BI, business intelligence, data mining, machine learning, data analytics is now the most coolest term. Then industry 4.0, Internet of Things. You see, it's the whole range of bullshit bingo if you want to play it. But there is something that we also ask our students in Big Data Management Analytics lecture, because that is something that characterizes big data, this field. There are the 4 Vs. Actually, originally 3 Vs, then it got 4. Now I think we have even 7 and 8 Vs, but what remain kind of persistent are the 4 Vs of big data. Big data is characterized through these 4 things. Volume. So we have data from many sources, volume on our HDDs, and we have a huge number of instances, like in terms of number of rows in our tables, or a huge number of features of dimensions of columns that we observe there. This is what we have here. And we have velocity, which means data is arriving and also changing at a potentially high speed. And something that addresses both of them, volume and velocity, is, for instance, CERN, the Large Hadron Collider, LHC. There we have an insanely huge amount of data, so massive volume, at an incredible speed being recorded through a lot of sensors that constantly produce the data, and a lot of communication. However, communication is a problem. You see it. So whenever we are having a data stream, we don't want to shuffle data from A to B or communicate, do you have this or have that? We want to keep ideally communication to a minimum. And I wouldn't have believed it by myself if I wouldn't have attended it. At CERN, it was in 2017, We went there and we were asked them, okay, you have got several hundred terabytes of data per day in extreme cases. How do you send them through the internet, or not through the internet, but through your local area network? And they said, we don't. We plop out the HDDs, put them in a truck, and they really need a truck for that, and bring it from one building to the other building to an archive and plop out those that are necessary, those entries, those data sets. So here, as a good example of the LHC Large Hadron Collider, we have volume and velocity kicking in. Then we have variety that states like, hey, not all data is the same. Not all data is from the same data type. So data can be also represented in terms of vectors, in terms of sequences, in terms of graphs, of tensors, and whatnot. For instance, if we have a molecule like caffeine, my favorite molecule, if we want to represent that as a, we can represent it as a graph, as a network, like each atom is connected through an atom bond with another atom, or we can represent it also as a vector. There are certain embedding techniques like mol2vec. It's a relatively old method, embedding method, which translates a graph structure of a molecule, 2D structure, and also 3D, into a vector representation, 300-dimensional vectors that are representing those things. And, well, in variety, different sources rely on different formats. So if you have different sensors, different sequencing machines, different whatnot, you may have different formats that capture different data or different types of data. So this is what we have under variety. And veracity, well, that refers to the fact that if we have data, we may have data that is unsecure or uncertain. In which sense? Well, the input that we obtained may be noisy, manipulated, or even misinterpreted. And we consider data objects as samples, not as facts. So whenever we have a record, we have measured something, it's a sample that has been drawn, but it's not a fact that we have actually. Excuse me. And here again, the 4Vs, this is something from IBM. Here's what Professor Kröger once wrote. I do not get any money from them, me either. And here we see again volume, velocity, veracity, variety, and some facts that are, however, quite old. Because this is from, I'm not sure, 10 years, 8 years old. And now we get into this wave from data, the raw data that we collected from sensors or whatsoever, up to the final knowledge, this KDD pipeline by Fayad et al. We say that raw data is often big, somehow, depending what we have. In CERN, we have, like I mentioned, several hundreds of terabytes. However, during this data science process, like all this data cleaning, then this data transformation, selection, projection stuff, it shrinks. It's like some ice cream during summer that's melting down in your cone, in your ice cone. So if we have like raw data and we pre-process it, we get less data. And then from that pre-processed data, only the usable part for our tasks, like only the relevant columns, the relevant rows, it gets even less. And even if we can label it, if we have some domain experts, people from climate science, people from biology, physics, whatsoever, who say, yeah, this one belongs to this class, this one belongs to that class, this one is an outlier, that amount is even by far, far smaller. So labeled data is like the true gold, because nowadays we truly are drawn in data, but having high quality data, that is kind of like a challenge. And lastly, for complex tasks, high quality data is often still small, so not enough labels, noise, irrelevant to high resolution, especially in terms of like deep learning architectures. They require large amounts of data. There are some exceptions to it, but as soon as you're going for deep learning method, if you have 20, 30 samples, can be difficult. On the other hand, deriving patterns on 20 or 30 samples, how trustworthy is it? What has been learned so far? And there are certain, how to say, like consequences, because the originally huge, vast amount of data has melted down to this tiny amount here, or this one here, usable part. It fits in the RAM in your main memory, so you can easily go ahead and run Python and R scripts and whatnot. And big data systems, they support the first step in the process, like pre-processing, shrinking the data or whatnot. But before the age of big data, in ancient times, we had the emergence of relational database management systems, short RDMS and RDBMS, okay? And some history, props for Simpsons, Old Man Yells at Cloud. In the 60s, IBM developed a hierarchical database model. It was a tree-like structure, and the data was stored as records that have been connected by links. And here, forget about it. Just in case if your grumpy grandpa is telling stories, those were the days. And in the mid-80s, we have a rise of relational database model. So the data is stored in a collection of tables consisting of rows and columns. That was new. That was the hit, the coolest kid on the block. We had strict relational schemas, the so-called first normal form, meaning that the entries are atomic. So inside of a cell of your table is a value and only a value, not an array of values or a table within a table within a table. And SQL became the standard language based on relational algebra. So it is not only any language or a language, but a language that is founded on some former has some form mathematical foundations. So relational database management systems, they became and up to now still are the de facto standard for managing corporate data that we have here. And is also advisable to do. I mean, for proteins, we have the PDB, protein database. For genes, we have like the gene bank, for instance. There are many more. Or for what else? For even law text, we have the URIS as a database, and so on and so forth. And nowadays, also in engineering, they are going to establish something like that. And currently, I'm at a conference, so this is why this weird band I'm carrying around. And what we propose, for instance, is to create a database of algorithms, of data mining machine learning algorithms. So it brings the benefit. You probably have heard about Google's AlphaFold, a formidable way to predict the 3D structure of proteins. It is undoubtedly a great, okay, some applause, not for me, it's some great tool for predicting the tertiary structure. However, it is only as good as the data it has been fed with. And the data it has been fed with was the data from the, for instance, protein database. And so databases are a valuable way for even for now, or especially also for nowadays, deep learning architectures to train them, to optimize them for prediction or pattern detection tasks. What are some properties of this relational database management system? Well, initially they've been designed for transaction purposes in mind. For instance, of daily business companies, like if you're driving by train or by airplane, flying by plane, that you have all these transactions, who booked which train ride or flight, and so on and so forth. Financial transactions, you mentioned it. And we have data consistency on the one hand and availability. So the data should remain consistent. It should be highly available and fault tolerant. These are the demands, because if your data is not consistent, it's of no use. You cannot trust your data. If it's not available, it's also of no use. You cannot access it. So what is the database then good for? And it should be fault tolerant. So if something is broken down, the database is not completely messed up or lost, but you have some recovery mechanisms. And also imperative for that is like short read-write operations on the data. You even observe it nowadays, the importance of short read and write operations in the sector of, for instance, cryptocurrency. So you have like Bitcoin, you have like Ripple and whatever they are called of. There are many of them, Hedera, whatsoever. They have one thing they are kind of like bound to. They are convincing or reliable for money transaction if they are super fast for read and write operations on the data, beside the aspect of security and trackability. But if it takes too much time, well, then it's not the primary choice. And scale is also a matter. So usually we have in databases, relational databases, a range of megabytes to several gigabytes. We have some advantages. Data independence. This data independence means it is independent with respect to any operating system and underlying file system, if you have NTFS of Windows or journalfs of Mac or some btrfs from Linux, doesn't matter. It should always work the same. Or it's abstracted away for us as the users. And it has an advanced transaction concept called ACID. We'll get to it in the next slides. This implemented, and that takes care of synchronization of multiple users, of backup and recovery strategies, and so on and so forth. It's automatic, it's transparent query optimization. If you are running SQL queries, I mean, for most of them, like Postgres, MySQL, DuckDB is a quite young database system. DuckDB is an in-memory database, and it is in particular tailored for high speed or optimized for high speed. And there, and also in others like Postgres and so on, if you say explain, there's an explain command or key term, then it shows you how this query has been optimized and executed in the end. And this is some kind of like explainability. This is what currently in deep learning, it's lacking, or the people are doing research, and it's exciting times. But in databases, you can immediately see and understand, okay, what happened here with respect to the queries. And some basics on relational database, relational data model. Well, relational model uses tables, and this is the one and only way to structure data. A table represents objects with a given set of features. So every row is an object, is an entry, is a tuple, is an instance, is a sample. You see there are plenty of synonyms. You will see in 4 papers at least 6 different namings. Then we have, like, for columns, the attributes, the features, the variables, the dimensions. In most data mining machine learning, you see like the features or dimensions as its terms. And we have then the columns that they have atomic data types. So they are fixed lengths in terms of bits. The keys are identifiers. So if we have some keys, some primary key, they are like a fingerprint to uniquely identify it. Interestingly, or let me put it this way. And this is a question to you as a dear audience. Imagine I do not define in a table any primary key. I'm super evil. No primary keys. What will happen? Or does it even work? Can I be able to create a table that has no keys? Any ideas? This was something that, if you wish, go ahead and check it out with something like, I type it SQL Fiddle, I think, at least during my study time. This is something I can start creating tables. Or you can download something like SQLite. This is also a very compact and lightweight SQL engine, database engine. What happens actually, if I'm really evil and say, no primary keys at all, under the hood, so if we have 2 rows that have exactly the same values, like here we have exactly Munich, exactly the same number of population, exactly Bavaria again. What may happen is that, or not may, what happens is that under the hood, it will have a hidden index, a hidden ID. This Munich will get the ID 1. The next Munich, if there would be a second row of that content, would get the ID 2. So even if we do not specify by ourselves any primary keys, depending to a certain degree on the database we use, but let's assume MySQL or SQLite, it will create under the hood its own identifier. So these are the single tables that we have. And here we say that this header is the schema, and the single rows, the single tuples, are the instances. And what we see within those single cells are the values of the attributes, of the features. This is, however, what we had so far, only a single table. We can have several tables, hundreds, thousands of tables. And the relations between those tables they can be achieved by, for instance, foreign keys. So through the concept of keys and foreign keys, we can connect several relations, several tables with each other. Well, there are some more things about the keys of the relational data model. So each row must be uniquely identifiable. Okay. Different to programming languages, so objects and object-oriented languages like Java, C#, and so on, they're identified by identifiers or references. In the relational model, rows are identified by attribute values, so what's written in the cells of a row, for instance. And one or more attributes must be flagged as keys. I mean, in extreme case, if nothing is flagged, depending on the database, they may have their own primary key. And the values of these attributes must be unique. So if we specify, if we say, hey, you know what, this P and R or this A and R, we want to have them as primary keys, then they are not allowed to appear non-uniquely. So keys identify rows uniquely, and keys can be used to refer to unique rows from other tables. Like here, we have Abteilung, oh, has not been translated. This department 01 refers here to department number, Abteilungsnummer, and this is like bookkeeping or production or marketing. So the value in one column of one relation refers to a primary key, to a foreign key of this relation, of this table. And let's have a look at this table. We have a lecture number, title, and term. And here, this underlined means that they are key attributes. So we need both to have some unique stuff. Because here we have 13 and 13, so that's not enough. We need also to know the term. With the term together, then we can identify each row here uniquely. Well, what's the problem with this? We need to store the title of a lecture several times. We have here machine learning, machine learning. Now this is only 2 times, who cares? But that'd be not 2 times, but 2 million times. Well, that eats up a bit of memory, I would say. And for any 2 rows, R1 and R2, it holds if the value of row R1 and R2 in lecture number are the same, the values in title of R1 and R2 must be identical too. So if here is 13 and here is 13, then here must be also machine learning and machine learning. And this here, so the title being dependent on the content here of the lecture number and being the same. So we have a mapping. 13 is machine learning, 12 is Java 101. This is coined by the term of functional dependency. So here, title of the lecture depends on the lecture number. And if we consider that we want to change the number of the lecture for whatever reasons, bureaucracy at its best, to introduction to ML, so no longer machine learning, but introduction to ML instead. Well, in this case, we need to do this update several times, go through all the entries that have 13 and update it from machine learning to introduction to ML. And if we are not aware of this, that this title is redundant, we may have missing some tuples. And one is machine learning, the other one is introduction to ML, and then again machine learning. And there you go, we got the so-called inconsistency of the data. So redundancy wastes storage. Well, really? Yes, really. I mean, it's obvious probably to a certain degree. But the problem is even more severe. They can cause anomalies, like as we have seen here in this insert case, if we name this one not machine learning, but introduction to ML, and leave this one to machine learning. How can we approach this? Well, here is normalization to the rescue. By the definition of keys, we can say any entire row of a relation is always functionally dependent on the key. So there's one thing. And these function dependencies are welcome, so they do not cause redundancy because these keys, they are used uniquely to identify tuples. But there may be more function dependencies. As a concrete example, an attribute that we have can be functionally dependent on only a part of the key. So not both columns, for instance, that are the primary key, but only one of the columns. So for instance, the title depends on lecture number, but not on the term as we had here. It does not rely on that. And well, yeah, I mean, we can do that. But then we have here a so-called partial functional dependency. So an attribute or a column that may be functionally dependent on another attribute, or another column that is not part of the key. This would be the third flavor. This would be then the so-called transitive functional dependency. So if you have a column that's dependent on another column, which is not underlined, which is not a part of a primary key, then we have a transitive functional dependency. And the purpose of normalization is to get rid of all those functional dependencies, partial one, transitive one, to get away with them. And all those functional dependencies that are not related to the properties of the key, because, for instance, some of them can cause anomalies. And in theory, there can be more functional dependencies to take care of, but in practice, only those functional dependencies like the partial or the transitive ones to the second or third normal form are erased by normalization, like the first normal form, second normal form, third normal form. There's also a so-called fourth normal form, Boyce-Codd normal form, fifth normal form for temporal database and whatnot, but they are quite rare. So to fix the original problem that we had before, we can say, well, let us make from one table two tables now, one with lecture number and title and one with lecture number and term. The advantage that we observe here is if we change here machine learning to introduction to ML, we do it once and only once, which means in the end that whatever we have here for 13, it always refers to the same entry that we observe here. And well, the schemas, they do not have any functional dependencies of attributes on a part of any key candidate, and any functional dependencies of these attributes on non-key candidates, candidate attributes. Those type of schemas that they have not functional dependencies on a part of any key candidate and also on non-key candidates, so that are neither partially functional dependent nor transitively dependent, they are called third normal form schemas. And that's basically the whole magic behind 3NF. So they do not, so schemas or tables, relations that exhibit no partial and no transitive functional dependencies are in third normal form. And some small words on SQL. Well, SQL is the programming language for the database management system. It's a highly matured API. Why? Because it allows to define data structures in terms of the schema. It allows to store or manage data, inserting, deleting, or updating data. And it enables to manipulate and query your data. And there's something to be good in SQL. You need approximately 2 weeks, plus minus. Everyone learns different, and then some continuous practice. And now some feature that is, as we mentioned in the earlier slides, is also inherent to the transactions is the transaction concept. So the key to synchronizing multiple users, imagine you have a train platform like of the, what do we have, or of the Deutsche Bahn, of the Austrian train service, of the Czech train service, or whatsoever. And they have to handle day by day several hundreds of thousands of users. And to ensure availability, because it would be terrible if the platform is not available, is down. And so it should also have the capability, if it crashes, if it faces errors, that it can have some mechanism for recovery. And for that, we have the transaction concept. So typically a user, some program or some session is a transaction. Like me as a user logging into a platform, I'm a transaction TI. And a transaction is a sequence of read and write operations which preserve a consistent database state. So it says we go from one consistent state in a database to another state, like from one snapshot to the next snapshot, it should remain consistent, nothing should break in between. And transaction management of such a database management system has two purposes. One is the synchronization, like coordinating the different users and their access. And the second one is the recovery, which is a solution to crashes and other types of errors. And this transaction consists, we have a database in consistent state. So we have some temporal states, and after the transaction, every transaction is atomic, it has to get into a consistent state again. If not, it will have some automatic rollback mechanism to get back to the last consistent state. And now, here. Now some example for a transaction concept. Excuse me. So we have here some crash at the bank, which would be really horrible, but can happen. We transfer 200 euros from the account of Huber to account of Muller. There's a possible schedule. So we have either a decrease, so we first decrease the balance of Huber by 200 euros and then increase the balance of the other user, Muller, by 200 euros. And what can happen here is we have here Muller with 1,000 euro balance and Huber with 1,500. And we see we have here now Huber got subtracted or withdrawn the 200 euros from it. So we got 1,300 and then a crash happens, system crash. Can happen after all. And just a second, I have to. Now we should have a bit more silence. And yeah, so we've got here a system crash. And a second example that we have here, we have some uncoordinated users at the airport. So the flight operations FO prints out the names of the passengers and the number of passengers of some flight like Lufthansa 001. At the check-in, it checks in another passenger, one of these late arriving Hans circles or whatever. And Professor Kröger wrote, I'm really jealous because of their status. Well, okay, who am I to judge? So the possible schedule is the flight operations prints out the list of name, the check-in, checked passenger pantomime in, and the flight operation prints out the number of passengers. What went wrong or can get wrong? Well, the flight operations gets inconsistent information because pantomime is not in the list, but is counted for. So it may happen at a crash that we have this name, if after the second step it crashes, that we have like an increase of the counter, like flight operation says it's not 20 passengers, but 21, but this name of pantomime is not in it. Can happen. And to ensure that it gets back, that the database reverts to a consistent state again, we have the so-called ACID principle, or to have this reliability. This defines a set of properties for transactions that shall be ensured within a database. And we have atomicity that states a transaction either runs to completion, or if it does not, it has no effect at all. So it's you either complete successfully or get back to the last consistent state. Consistency, a transaction preserves any integrity constraints, because for database, you can call upon some so-called constraints, like for instance, in this field or in this column, it's not allowed to have any certain value, like negative values. You don't want to have a negative year or a negative weight or something, as an example for one type of consistency. Then we have isolation. So even though transactions are executed in parallel for performance reasons, the effect of each transaction must be the same as if they have been operated serially without concurrency. So you have to ensure, even if this concurrency does not take place, you'd still have the same order as if, or no, even if you have concurrent processing, it should be operated the same way as if you would execute it in a serial manner. And lastly, we have the durability. So we say the effect of transaction that successfully completes gets a commit status from the system and must remain in the database. It must remain persistent, durable in case of a later crash, error, and so on and so forth. And let's see. So the big picture about all this database management thing. Well, relational databases are the de facto standard when it comes to managing data. They offer a mature, they exist several decades and a powerful technology. and are superior at least to file system solutions, to have some Explorer or some command line solution. Data is modeled in tables, just like in Excel tables, but please don't use Excel tables. I mean, we had some case in bioinformatics during this human genome revolution thingy. Ooh, the people started putting things in Excel. Excel with any new version did some weird stuff. They interpreted automatically some columns anew, and then they were incompatible between the different versions. No, just don't do that. They suffered in the end and had a great deal to porting it to a relational database. And consider normalization for non-redundant anomaly-free storage, as it is the one holy grail, the paradigm to ensure secure, consistent, available data source with multiple users and through the transaction system that they have with parallel access. And SQL is a powerful standard API or language for data management, for modeling, storing, and retrieving your data. So far on the relational database stuff. Now let's make a transition to a small intermezzo, like managing spatial or geospatial data. And well, geospatial objects, they have spatial coordinates, usually 2D, sometimes 3D, like X and Y coordinate, or latitude, longitude, altitude. There we have the 3D. There are types of attributes like spatial ones, coordinates of a point, longitude, latitude, area of a polygon like we have here. We have some topological attributes like polygon 1 and polygon 2 are neighbors to a common face, K1 for instance, and we have some thematic attributes like polygon 1, for instance, here is a cornfield, point 2, polygon 2 is the city hall, and so on and so forth. So this is what we can. This list is by no means complete, just some examples on that. And we have in spatial coordinates associated to that some kind of realms. So the challenge of the Euclidean space here 2D that we are looking at is we have point coordinates, XY coordinates, that are element of the real numbers. And the computers store the real numbers as so-called floating point numbers, floats, that have a certain precision. However, not all real numbers can be represented as floats. And as a consequence, the intersection of, for instance, this intersection PS that we have here of the two lines L1 and L2 may not be recognized, may not be represented by floats. There are, however, some workarounds. And well, interpolation to the next float produces inconsistencies. So PS is not part of P1 nor of P2. So the idea or the workaround intended to just interpolate to the next float can happen that it is no longer located on the intersection at all. That is off. There are, however, some solutions. In 1994, Schneider and Gütting had one idea. They said, given a set of points PR that are from Cartesian product, a subset of a Cartesian product of natural numbers, so basically a grid as we see it here. A realm is a set of points P from this PR over here and non-intersecting line segments S over PR. So we have basically this. So intersections of line segments must be on a grid point in PR. So if we have here a true intersection like here, it must be located on one of these grid points. So a realm can be interpreted as a planar graph. The points are our nodes, the edges, or basically the edges are the edges of the graph, are the line segments, this line segment, and we have it here. One interesting observation, it is dependent on the resolution of our grid. Here we have a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 by 10. If we have a 50 by 100, then we may have a much finer grid, but also a higher computation time. If we have lesser lower resolution of the grid, we may have faster computations, but again, we may miss things. We may miss intersections or be imprecise. And modeling spatial data, well, in geoinformation systems, in GIS, spatial data is usually mapped or a relational model, like we store all information in tables. There are several different ways that can be done. One is the so-called spaghetti model. So each object is a sequence of distinct point coordinates, x, y coordinates, for instance, border points. Each object is represented independently, which means, unfortunately, we get a strong redundancy of the points. And simple model, it's a simple model with no explicit topological properties, so no holes in a polygon, like a donut shape, if you want to have that. Then there's something more modern and without the drawbacks of the previous model, the Tiger model, topologically integrated geographic encoding and referencing model in the mid 80s by Marx. And there we have like complex, non-redundant, normalized model. And we have different data types for points, lines between points, surfaces, like closed set of lines, cover, like union of surfaces, and so on and so forth. The problem of normalization, well, it's a high cost to get all information of more complex structures. Result of a query does not return an object, a line, but a set of entries, like a set of points expressing a line, 2 points specifying a line. So that's a challenge we are going to face here. And as an example for a Tiger model, we have here, for instance, OID, the polygon ID, and the Q meter. So for parcel, and we have here for polygons, the polygon ID, the KID for the edge, for the Kante, and for the edge, Kante, why is this in German? For the edge, we have the edge ID, KID, we have from, we have to, and these P's are the for points, PID, and we have here like X and Y coordinates of the points. So basically, you see it's a hierarchy. You say points can assemble to edges, Kanten. Several edges can assemble to polygons, and several polygons can assemble to a parcel. And so that's the table of the cover that we have here. That's the table of the surfaces. That's the table of lines or edges, and that's the table of points. There is, however, something, as you've seen with the previous approach with the grid, it's a matter of resolution. And sometimes resolution can be quite important. It's something that one is tempted to ignore to a certain degree. So let me show you something that highlights this. And I'm not sure. Can you see the Google Trends webpage? Any thumbs up on that?
I know we still see the presentation, I believe.
So okay, then
Or
I just.
it's a Google Draw. I'm not sure, sorry.
Oh, no problem. No, that's great. Thanks for your feedback. Do you see this Google Trends?
Yes.
Yes, now yes.
Great, thank you. And now, this is Google Trends. It shows you in relative numbers how often which key term has been queried. And let's look for the key term party. It's party time. And okay, currently I'm in Portugal at the conference, but let's take Germany. Seriously? Okay, Deutschland, fair enough. You see, during the last day, the relative amount of searches for the term party. You don't see something special. You see maybe here there's an increase of queries around 3 a.m. Okay, why not? Now let's have a look at a different resolution. Now we don't look on a 24-hour basis, but on a 7-day basis. Now we see people are querying for party during midnight. Isn't that too late? Okay, I'm probably too old for that. But we have here 0, so midnight, 1 o'clock, 2 o'clock, 4 o'clock. They are looking for party. Why not? Okay. Then let's have a look for another keyword, because sometimes terms can relate or correlate, not have a causal relationship necessarily. So correlation does not imply causation, but they may have a relation. Now let's have a look at the key term called ibuprofen. And whoa, lo and behold, We see here, for instance, at midnight, we had party, a peak. And here for ibuprofen, we have a peak at 2 or 3 or 4 o'clock, which makes sense. I mean, you first party hard and recognize, oh, shoot, I'm going to have the hangover of my life. And here the same. You have here a high querying for party in a quite long span. So here it's between midnight and 5 o'clock. And here you see a small peak at 3 o'clock querying for ibuprofen. Here I have no bloody idea what happened. Here, I mean, we have the peak for blue for party, but we have two peaks, two insanely high peaks for ibuprofen. To be honest, I have no idea why it's related to that. I'm not sure that there was any special holiday or public holiday, but well, we can call this is a so-called anomaly. And you see here, so it's with a certain temporal shift of a few hours, we see the more frequent search for the term ibuprofen. Now, what happens if we look for the term sick leave? I think it's Krankschreibung. Yep, we also recognize something here. So as example, we have here for party at 1 o'clock, a huge query. Then we have here at 4, 5 o'clock for ibuprofen, a larger amount of queries. And at 6 o'clock for sick leave. So first you party hard, then you say, oh, I've got going to have the headache of my life. And then you say, you know what? I need to get the doctor. I can't work today. By the way, we are not promoting alcohol consumption. If you want to drink, drink responsibly. And I hope everyone here is above 18, what should be the case, I think. But this is what we have here. So we have like several of these, and you can even add this by any other, but you see those patterns occur on a weekly range on 7 days. You see patterns emerge that otherwise on a single day would not emerge. And we can even, oh, there's a question. Okay, and we can even have another key term. I mean, if you need some baseline for a party or for drinking, so let's have some döner. Why not? Do we observe here something? Wow. Okay. At which time? We observe at 7 p.m., roughly roundabout, and here also at 7 p.m. So we have it's döner time, so to speak. Also 6 p.m., fair enough. I mean, it's during like here a dinner time, makes sense. And if we remove this term, you also see certain effects that may be overseen. Here you see a peak, or here you see a peak. Why don't we see here a peak? Like for sick leave, we don't see any peak. Well, which day do we have? It's the 29th of March. The 29th of March that we have here is or was a Saturday. So Saturday and Sunday, for those people that queried that, maybe no job. So no need to look for that term. So these are also things that are very subtle, but get visible in such trends. So it's a matter of, yes, of temporal or spatial or whatever resolution. Even we can go to 30 days. And for 30 days, we don't see that much. Interestingly, some others flatten out. We just see here something, but we see here some peaks for party. And if you look at those days that are close to the weekend, like 22nd or 29th, the 29th was which day? It was the Sunday. So it's from Sunday to Sunday to Sunday. Just a small excursion to this realm that we have here. And so keep in mind, besides all this, I mean, geospatial thing, fair enough. But one thing to keep in mind is resolution can matter or can be of certain importance. Now, managing big data from relational database management systems and managing geospatial data. Now let's transit to managing big data. Well, with this advent of Web 2.0 in the mid-2000s, these whole database management systems were kind of like urged to scale up with this vast amounts of data. And there are different types of scaling. Well, we've got the so-called vertical scaling. You take your single machine like my laptop here or my PC at home and beef it up, put more RAM, more CPU power, more of everything. Yeah, more HDD. However, it's limited in space because you cannot beef it up infinitely and it can be quite expensive. And There are some typos in this I have to go through. And there's something called horizontal scaling. So we use many machines, and those many machines form like a cluster or a grid, and it's limited by the cluster maintenance because Google, for instance, or Alphabet or Meta, they have insane huge amounts of machines, and those machines will fail, and they fail. So you have to have mechanisms to show you that they fail, so-called heartbeat signals. You need to have the capacity to replace them quickly, to have some replications. So if one of them fails, you replace them by another machine. The machine takes the replica from the others to have the same replication level, the same redundancy level of the data for faster computation and being stable or secure towards machine failure and so on. So between those vertical and horizontal scaling, this horizontal scaling won the whole game. And that was like a catalyst for this whole NoSQL, which stands for not only SQL movement. This doesn't mean no, 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 but it means not only SQL in the mid-2000s. And the problem that motivated was that these relational database management systems, they do not scale well horizontally. So all these big players like Google, Amazon, and so on, they developed their own storage systems. So not only SQL systems, databases were born. And today we have the age of NoSQL. So we have several different NoSQL systems, more than 250. Some of them die out or are discontinued. Some new of them emerge. Well, and there is no unique definition, but some kind of like rough intuition or characteristics for NoSQL databases. We have horizontal scalability, like cluster friendliness. They should be non-relational, or not should, but they are non-relational. They are distributed, so they are designed or by design for parallel settings. They are schema-less in the sense that they do not have like header like in our SQL tables, and they should be open source, at least most of them. This is not something we observe everywhere. And the most important part, this ACID thing, this holy grail of relational databases is no more. Instead of ACID, we have, pun not intended, we have the term base, an artificial concept for NoSQL databases, which says they are basically available. So the system is generally available, but some data might not at any time due to node failures because we have a distributed setting. If the one machine fails, some part of the data may not be available, but through replica, through redundancy, they minimize this issue. They have a soft state, so the system state changes over time. Stale data may expire if not refreshed, so you have data that is no longer valid and eventually consistent. The system is consistent from time to time, but you cannot expect it to be always consistent, so updates are propagated through the system if there's enough time, because it takes time to distribute the changes, the updates throughout the entire computing cluster. So Bertha's place is some kind of opponent to ACID when considering consistency availability spectrum, which we see at the triangle example. So two types of consistency are corresponding to distribution type. We have data sharding and data replication. So logical consistency, which corresponds to data sharding. So the data is consistent within itself. So within these parts, it is consistent. We have data integrity as a consequence, and replication consistency, as we have here. The data is consistent across multiple replicas. So we have this red part being in this database, in this yellow part, in this and this database. And as a consequence of this, we observed the so-called CAP theorem or Brewer's CAP theorem, which is this triangle of consistency, availability, and partition tolerance. So any networked shared data system can have at most two of these desired three properties. So a system can be consistent available, but then it's not partition tolerant, or it can be consistent and partition tolerant. But if you've enforced to be consistent at all time and partition tolerant, you may sacrifice availability. So the theory. So we have here any partition system that's horizontally scaled need to give up either perfect availability or perfect consistency in this CA edge. So all clients always have the same view of the data for the consistency, and in availability, each client can always read and write the data. This is what we have here. And now, The four main NoSQL models that we have out there, they are key value stores, document stores, wide column stores, and graph stores or graph databases. And well, the key value stores are the most simple form of a database system. You have, like in a hash or dictionary, a key and you have a value. Behind this key, this ID, you have a file. Behind this key, you have an integer. Behind this key, you have a picture of a cat. Great. And well, values, they can be of arbitrary format, like files, numbers, pictures, whatsoever. There are extremely heterogeneous systems. Some systems, they kind of allow the ordering of keys and even support or even enforce it. That has the benefit to accelerate, to speeding up the querying. And like range queries in some systems support in-memory data maintenance. Some use disks and so on and so forth. Examples for them are Redis or Dynamo, just to name it. Document stores, they store documents in form of XML or JSON files. They are semi-structured data records that have a homogeneous structure, and columns can have more than one value. So you can have an array of values. It breaks with the relational database where you had this flat structure where we said every entry is atomic. It cannot consist of an array or something. The documents include internal structure or metadata, and data structure enable efficient use of the indices. So examples for that are like MongoDB or CouchDB. And indeed, for masses of data and also some of the large language models for storing the data and querying the data and making accessible to the models, rely on some of these document store techniques. The wide column stores, well, the rows are identified by keys, and rows can have different number of columns, up to several millions, which makes them quite powerful in that sense that they support really high dimensional data. And the order of rows, however, is dependent on the key values, so locality is important. We have multiple rows, which can be summarized to families or tables. So you can have like a partitioning within this bunch of rows that you have. And multiple families can be summarized to a key space, like an address space, like all people living in that street from, what is it, like the Maple Street 1 until Maple Street 50. So you have an entire key space or street space. And the main focus here is availability. Examples are Cassandra from Meta and HBase. Lastly, we have something called graph databases, and they use the graph structure to store and represent the relationships between entities. As we see here, Alice knows Bob, Bob doesn't like Alice, Alice knows Carol, Dave loves Carol, and Dave lent money to Bob. Okay, fair enough. And where it's composed of nodes and edges, and each node and each edge can contain properties, so-called property graphs. We use this indeed within so-called the Connectome project that we had at the CAU. We took, or we created from lectures, so-called graphs, like almost like mind maps, put them into a database and made them in such a way queryable, so that if people type in certain keywords like distance functions, they see the lectures in which the term distance function occurs and the local context. Like in advanced data mining machine learning, distance functions is in the context of high dimensional data mining and curse of dimensionality, and distance functions in knowledge discovery and data mining lecture is for like the distance between two points or pairs of points for hierarchical clustering. So this is what we used for, because there we saw it is already a graph structure. It makes sense to use the properties that such graph databases have. So there's an entire family of different methods you see here. For instance, like CouchDB, Cassandra, Dynamo as a Cassandra as a column-based for NoSQL database is between the availability and partition tolerance. Partition tolerance, like the system works well despite physical network partitions, despite splitting of it. And last but not least, distributed data processing. Well, with these relational database management systems, especially in context of big data, database systems are difficult to scale. They are difficult to configure and maintain. The diversification in available systems complicated to its selection, and peak provisioning leads to unnecessary costs. The advantage of NoSQL systems is they are elastic scaled, they require less administration, at least they claim it. Well, that's debatable. They have better economics. This is what you read in some papers. What the measures that they use is they say it retrieves you faster the query result, or it has less computational complexity and hence saves you also money in terms of power consumption. Depends. 15 years ago, yes, nowadays the tides are turning, and it says it has flexible data models, flexible in terms that it is not bound to this rigid relational tabular format, but can be of any structure, like of hierarchical structures in document store or in terms of a graph, like in the graph databases. But NoSQL drops a lot of cool features that we had in databases, in relational databases. Well, we do not have real dictionaries, so no real dictionaries, but semi-structured models for providing metadata. Usually they're still hard to access without having explicit knowledge of the data model. The transaction processing is constrained by the CAP theorem, meaning that we cannot maintain this asset that is atomic, that is consistent, that is maintains integrity, and that it's durable at all times. And we have some limited indexing or efficiency. And this is mostly replaced with scalability. So relational database management systems, they are highly efficient. They are supported by index structures. There are a whole literature, a whole book series about index structures to faster retrieve your query results. But what is then left? Well, basically, we have storing massive amount of data in cluster environments, eventually consistent stuff, and some database-like APIs like CipherQL from the graph databases. And if we look at this, what we have left after all these cool things, transaction, efficient indexing, access control through transactions, if all this is gone, what do we have in the end? Well, what exactly are NoSQL databases so much different from classical file systems? Having your files plainly on your machine. Not that much, it turns out. We have to remember there is something about data science process involving pre-processing. If you remember this pyramid, like raw data, pre-processed data, then reduced data, and then labeled data. And in this data pyramid, the majority of analysis still run on files. So if you do your clustering, your classification whatsoever is still done on the raw data files that are read into your memory. Machine learning statistics and data mining methods usually access all available data. And most data mining and statistics methods require some well-defined input and not some semi-structured objects like in a JSON file. And this is one of the tasks to be done in pre-processing. So scalable data analytics often is already content with a distributed file system and not some fancy NoSQL engine. And analytic methods may be parallelized on top of the distributed file system. So to a certain degree, yes, NoSQL technologies are cool. And if you have some really specialized tasks, they are the go-to format. But you are quite fine when it comes to data analytics with your data distributed and massively parallelized on a file system. And here in parallel computing or cluster computing architecture, computing nodes are stored in racks, like in this rack, one node, a second node, a third, a fourth node. Nodes on a single rack, they're connected by a network, usually a gigabit Ethernet, as we see here. And here we see racks of servers and switches at the top at Google's Mays County data center. And there's some characteristics, like files are several terabytes in size. Facebook's daily logs, 60 terabytes, 1,000 Genomes Project, 200 terabytes, Google Web Index, 10 petabytes and counting. So the files are rarely updated. This is one thing. If the files are constantly updating, this is expensive. But if they are rarely or almost not at all updated or changed, so it's read-only, then you don't need really a transaction system. And well, reads and appends are common, so just keep appending the next rows in your file, then that's fine. We have Google file system, GFS, Hadoop, HDFS, Cloud, HDF5, Amazon S3, EC2, and whatnot. So what's the organization? files are divided into chunks, typically 60 to 64 megabytes in size, small bytes of data, pun intended, and the chunks are replicated n times. You want to have redundancy. Redundancy for two reasons. One, if something fails, you still have some others. If you're writing your seminar work or your bachelor or master thesis, you want redundancy. You're not going to save it on a single USB pen drive, which actually a colleague of mine did during my master's. He suffered a lot, but yeah. I mean, you know it better. You don't do it. And well, you have it for redundancy, for the purpose of safety against failure, or if there's some outage of the system that you still have the data available somewhere, and for the sake of parallelization. If your data is on one node, one computing node only, it will take a lot of time because this one node with the data that all the others need is like the bottleneck. But if you copy the data, then several nodes can at the same time compute on this data if necessary. Excuse me. So the chunks are replicated n times. In HDFS, the default is n equals 3. At n different nodes, the best case scenarios replicas are located on different racks, optimizing the fault tolerance. So how do I find these files? And well, there's a master node which holds a meta file directory about the location of all copies of a file. So this is the master map. And all the participants using the distributed file system know where these copies are located. So all the machines through this primary node, master, it was this master-slave terminology. Please do not use it. You have master and slave here. Instead of master of slave, you have primary, secondary, or computing node and like a managing node, something like this. In HDFS, the distributed file system provides high throughput access to application data. It has a primary, secondary architecture, so forget these terms. And it looks like this, quite a lot. So we have on a rack, we have several data nodes, and on the data nodes, we have several reads through a client and this name node. That one distributes and says, okay, here you can compute on that part. We have replications of all that. It's quite, I would say, complex to a certain degree, but yeah, it's basically about knowing what is when and which process requires what, and about replication, that we do not have all the data on one node, but distributed ideally across several nodes, across several racks, because even if a rack burns down or something happens, still the data is on some other rack. We have MapReduce and relational database management systems side by side. Well, MapReduce is capable to process petabytes of data, where relational databases gigabytes. The access is batch-wise in MapReduce and interactive and batch-wise in relational databases. In regarding updates, we have write once, read many times. So we're not expecting in a MapReduce setting for data analytics to write or to edit updates by any means, or quite rarely. Whereas in relational database systems, we have read and write many times, like for transactions for buying some plane or train tickets, for instance. The structure, we have dynamic schema versus static schema, and we have an integrity, low integrity via high integrity, so normalized data, and the scaling is linear. So linear scales with respect to the amount of data, where we have here a nonlinear scaling. And well, MapReduce versus HPC, because we have the high performance computing, the supercomputers that we have in the top 500 list. Just for the record, if you have not seen it yet, there's this top 500 supercomputer list. There you see the top 500 systems that are currently here. Nah, show me the list. I don't want to have that. Here, top 500 list. No, seriously? Okay. Here we see the current number one. They keep changing frequently. It is El Capitan in the United States. It has 11,000. No, this is 11 million. 11 million, 1,000 would be 11 million, 39,000 cores, 616 cores. It has a maximum performance of 1.742 petaflops, peak performance of 2.746. And you see also the power consumption, unfortunately. it is interesting that this one with a much lower performance has a higher power consumption. And this motivated not only the top 500, but the top green 500. And the green 500 is a ranking of those that are most efficient. This is not the green 500. Show me the list. There we go. Here, for instance, we see it's only 19,000 cores, but we see here a new unit, like how many gigaflops per watt is being computed. So this top 500 list is also something that frequently gets updated, like the top 500 list. And there is a run for getting not to petaflops, but the first exaflop computing systems. Yeah. And you see here is United States, Italy, Japan, Switzerland, Finland, and so on. You see the different countries. Yeah. And that gets back here. Well, now comparing MapReduce versus HPCs, well, accessing large data volumes becomes a problem in these high-performance computing systems, as the network bandwidth is the bottleneck, regardless which architecture they have, like the Dragonfly architecture or whatever it's called for the inter-process communication between the machines, it remains the bottleneck. It is kind of like solved through data locality by MapReduce, where we say, bring the computation to the data and stop shuffling data around from one node to the other. So the data flow must be handled explicitly in HPC by programmers, solved through higher level programming. Data flow is implicit by MapReduce. So in HPC, you have really to go there with some OpenMP or MPI message passing interface and do that in C, while in MapReduce, it's done through Java, Python as a high-level abstraction layer. And the handling of partial failures depends on the HPC architecture. In MapReduce, we have a shared nothing architecture, so no dependence of tasks. So detection of failures and rescheduling of missing operations is easy and conducted by the name node. The name nodes keep sending so-called heartbeats to the working nodes or to computing nodes. If there is a heartbeat not being submitted back, then it marks this one node as dead and will reschedule the data and replicate the data on other nodes. Reschedule the task and replicate the data. And well, in general, MapReduce is utilized to manage large-scale computations in a way that is tolerant of hardware failures, and you need that, considering that you have a lot of hardware that can fail. And system itself manages automatic parallelization and distribution, so I/O scheduling, as well as coordination of tasks. They are implemented and encapsulated in so-called map and reduce functions that are the two core functions, which are by itself not new. If you have had functional programming, Haskell, Scheme, Lisp, there you may have already faced or recognized the so-called map and reduce functions. Map, you apply an operation on every element of your data, of your array or list or whatsoever, and reduce, you reduce the values, you aggregate them through like summing up, for instance, all values of an array, or multiplying all values of an array, or computing the average, and so on and so forth. So a system has the capability to handle unexpected system failures or stragglers in automatic fashion. And the implementations of basic models that are available are Google's internal implementation, open source implementations like HDFS from Hadoop, and so on. There are plenty of tools for different things, for machine learning, for packaging and testing, for graph algorithms and whatnot. And yeah, there are, however, some limitations, so it's also not the holy grail. As you probably know, MapReduce is a successful batch-oriented program model, but there's an additional demand for processing modes like graph analysis, stream data processing, text analysis, and whatnot. So demand is growing for real-time ad hoc analysis. You don't want to wait until computation is finished, but you want to get a result within a matter of seconds. And analysis with specific queries, like including only subset of data with additional time constraints, is one approach to this at a real-time demand. The solution in Hadoop or MapReduce world is Yarn, yet another resource negotiator. And finally, not everything is parallelizable. And yeah, this is it, what we have here. As mentioned, this is a very, very rough and quick glimpse over the whole stuff. As for myself, I'm not really in the field of of databases or database management. My specialization is unsupervised machine learning, clustering, anomaly detection, or newly developed, designed in-between instance detection that we have. But I hope it gave you a glimpse or a rough impression of that. And finally, because, as I said, correlation does not imply causation. What is it that we have here? Causation. Spurious correlation. Now I get it. Spurious correlation. So this is a fabulous website with a certain entertainment factor. If you see here, you have like correlations, not causation, of course, not necessarily. And we have here the number of mechanical drafters in Colorado and season wins for the Denver Broncos. And we see here a correlation of 0.814. Or we see here number of registered Yamaha motorcycles in UK and annual email spam rates 0.903. Okay, so it's a correlation coefficient. Or air pollution in Wichita and tech resources stock price. And here we see not that a high correlation of 0.652. Do we have some others? There were some hilarious ones. Robberies in Alaska correlates with professor salaries in the US with a correlation of 0.922. But we think or assume that these two, robberies in Alaska and professor salaries in the US, have nothing in common. That's it. That was the overview so far. And are there any questions up to now, up to that point? As mentioned, if there are any questions beyond or above this data management stuff, if there's anything about like clustering or unsupervised machine learning and stuff like this, feel free to contact us, ping us, and maybe see you in Gdynia in May. And if there are no questions, thank you very much. Thank you for attending here, for being here. And yeah, sorry, it was a bit on the stupid circumstances right from the conference. So not the ideal conditions, but I hope you could still take something from this. Well, thank you. And best regards. Yeah, bye.